Hello everyone, and thanks for attending this talk. And first of all, I would like to appreciate and acknowledge the invitation that the organization of this conference on doctoral schools from the University of Galati had made me and gave me the chance to provide you with this topic of analytical design for PID control. This is in fact a quite specific talk about otherwise one of the central elements of industrial process control, that is the PID. And in this talk, what I will present is the results of some approach that we have been developing during the last year, and I think that it can provide some ideas or some ways of applying some modern approaches for what I put on the title, a classical choice for an element, a key element in industrial control, that is the PID. Okay, so the agenda is, first of all, I'll try to motivate why to still do research on PID. Okay, even it's a classical, why it's important to still do something and look for alternative and better designs on PID. Second, we will provide the definition of how we state the problem and provide a generic solution to this problem. And from this generic solution, we will see how, in a quite very simple way, we can derive and can obtain specific tuning rules for some of the process dynamics that are most usually considered in the industry. After this, we come to the second part of the talk, that is how we evaluate these tuning rules from the point of view of robustness and performance, and use this evaluation to generate what we call automatic tuning. I mean, tuning that do not have any degree of freedom, so it's very easy, very direct, very straight to apply. So it's directly tuning for PID for what we call a balance operation. I mean, it's a tuning that takes into account that at the same time the resulting control system has to be robust, has to have as a low performance degradation as possible, has to behave well for set point tracking, for set point following, and also for load disturbance attenuation. Okay, and at the end, we'll provide some concluding remarks. So, okay, let's start for the motivation. I'd like to start with a text like the one you can see on the screen. Okay, so this is the abstract of one paper where you can see these 3 points here. Okay, and if you take a careful read of this, you would probably recognize that this abstract probably could be a paper of you if you are doing research in electrical engineering on control, definitely. Okay, so on this abstract, it was stated one of the key questions that people that is doing research in control is trying to get, and is how can the controller adjustments, how the settings of the controllers can be determined for any control application. And this determines a universal question, okay? Any control application, not just a very specific domain, but any particular domain. And the way that this can be achieved is by using a model-based solution. And this is the third point that is stated here, is that the settings of controller should be determined before it is deployed on an application. So it's not a problem of going by a trial and error on a specific application. So you can get, if you have an analytical model of your process, you can get the determination before you apply it to your process. So even this is, or you can think this is quite new. You can forecast that which paper is this one. Okay, so if you are on the world of PID or paper of world control, then you may say that this is a paper of the last years, but in fact, this paper comes from the 40s, so it's almost 80 years ago. Okay, and it's completely formulated in a very, very modern and actual way. And for more information, if you, with this data, you have not guessed which is this paper, it is the famous paper of Seeger and Nichols, so probably one of the most cited papers in control. Okay? It's the optimum settings for automatic controllers. And in this paper, they started that for a controller that was already applied in industry and was really on the practical domain, started the search for research on PID by the way of looking for ways of getting the tuning of the controller. Okay, and this was the starting point that has been developing till our days right now. Okay, so 2 points were on the previous paper that even today in some of the papers that you can get on and also in news more related to the application, you can find this part of the first of all resilience of PID, and this is one of the main advantages and points that people from a practical point of view is like this, and is the PID is the kind of controller you can set it and forget it. Okay, and probably it will not be completely optimal, but it will keep the system working quite well. I mean, well enough. Okay, and the other thing is universality. So PID can be applied, or you can find it applied to a very wide spectrum of systems, from temperature to speed, mechatronic systems, biological systems, whatever. Okay, so the reason is that if today PLR didn't exist, so probably we would force it to invent it, because even with the modern applications that you can find of technology, factory automation would be very limited without a controller like the PID. Okay, so it's really the piece of the solution. From going more to the theoretical part, this is the result of a survey that was published in the IEEE Control System magazine in February 2017, and a series of industry-related partners were asked about to rate somehow the industry impact that was perceived by the industry committee of the IEEE, and if the technology, in the sense that PID, model predictive control, robust control, you can see the list here on your left, has a high impact on the industry or not. And definitely PID is the only that the result is binary. Okay, it is 100% with no doubt we're stating that PID control has high impact. Okay, while the rest, the perception is more subjective and is more critic. Okay, so definitely any advantage that you can get on PID will find his impact on the industry. Also from the pure research point of view, there has been already 3 conferences fully devoted to PID. The first in 2000, second on 2012, so 12 years were stated from the first one to the other, and the other one just 6 years after 2018 was recently in Ghent, and so we hope in the next years to have the fourth one. Both the 3 conferences were IFAC conferences with all the results completely devoted to PID, so it is a proof of the interest in them. Also, this proof is contrasted with the data that you have if you perform a bibliographic review. Okay, so I was taking Scopus data on publications related to PID, and you find that you can see that along the years, the number of journal publications that are the yellow ones are continuously increasing. Okay, as the time goes on, so the research interest on PID is still very, very, very appealing. And in fact, every time that there has been an event like a conference devoted to PID, there has been a boost in the number of publications. So you can find after every conference a boost on the publications. Okay, so there is a kind of exponential growth every time there has been a specific event on PID. So there is a continuous research interest that puts on the table that it's important to get PID control systems going and functioning in a more efficient way because of the impact that they had in industry. So the continued interest, we can state that comes both from the practical point of view and from the research point of view. Okay, so here you have some points that has been stated from the practical point of view, that they were of interest from the operator and also from researchers. Okay, from researchers there has been some claims about you should include robustness, you should incorporate the different trade-offs, and sometimes it is put it as a question that if you really what you want is really the most optimal, or maybe if you go suboptimal, then you can include some other benefits into the tuning. And in fact, what is one of the characteristics that is particular of PID is the fact of tuning rules. Okay, so the mix of all these points here finally melt and concentrate in the form of a specific tuning rule. And this tuning rule is what concentrates the way that you finally get the tuning of the controller. And this is a particular point of PID that is the one that makes it very, very appealing. Okay. So finally today, the PID scenario is much more constrained than the one that Seeger and Nichols had 8 years ago. And this is, it's somewhat natural because, systems have been continuously be asked for more and more. So now we are asked to a control system to behave well, both for set point tracking and regulation for load disturbance. You will be asked for robustness. You will be asked for as simple as possible formulation for the tuning. You will be asked for a trade-off among all these actions, measurement noise, etc. So the idea is that we need to think in a different ways to put all of them, or at least as much as possible of these considerations, such that the overall design problem can be stated in a simple possible way, and then you get the corresponding solution. So if you can deal with all of them in a joint way, so it must be much better because it provides a more simple and straight way to the design. And this is what we will try to do here. Okay. And we will try to do here by introducing two modern advanced control approaches and use them to design the PID control. Here we use a mix of H infinity to state the problem and internal model control to solve the problem. Okay, both of these approaches, modern control approaches, has his pros and his cons. Okay, so if you know with H infinity, it's not an easy theory. Uses to deal with high order controllers, but otherwise it's quite good for tackling of robustness. But internal model control, on the other hand, it has quite good industrial acceptance. It comes with a quite simple or accessible analytical formulation, but it provides not really good performance for load disturbance rejection. Okay, so every one of them has its pros and cons. Some of them you have here. The list can be longer, but the idea is that by using both of them, we will mix and state the design problem such that at the end you get what we call analytical robust PID. Okay, so how can we will do this? So we will state what is now in H infinity control the weighted sensitivity problem, and so we will state an infinity norm optimization of the weighted sensitivity, and the idea is to put the tuning of the problem in an appropriate way of parameterizing the weight in such a way that with this parameterization we can deal with the problems of interest about the performance on set point tracking and regulation, and at the same time with the trade-off between robustness and performance. We will solve this problem using the internal model controller and then get the solution and interpret the solution in terms of the PID controller. Okay, so this is the main map of what we'll do here. So how we state the problem? Okay, so we formulate the problem and get the generic solution. So the problem is stated in the following terms. So this is the basic single input, single output feedback control problem. Our plan will be assumed to be second order plus time delay. This is the formulation of the PID. Even you have ideal derivative term, in all the results we use the filtered one. Okay, so we use this one for the theoretical development because we avoid the derivative term. It gets more easy and more accessible way on the analytical derivations. Okay, and as you will see, we consider output disturbance, input disturbance, reference all the different signals that we will need to trade off on them. And very important, second order plus time delay plan, where usually one can find in the literature just first order plus time delay. Okay. How will we solve the problem and then generate what we call the different specific tuning of the specific cases? So we will solve the problem for what we call the base case. Okay, so this red shadow case, as we will be referred later on, is our central problem. So our central plan will be this one. And the idea is that if we are able to solve the problem for this plan, then with slight changes in the model, the corresponding generic solution will inherit the corresponding slight changes in the model. And then the corresponding solution will go to the particular cases. So we will solve the base case and get this as what we call the unifying tuning rule, because it will be the more generic tuning rule, and then particularize the generic tuning rule on the basis of some particular cases. Okay, so if we just set one of the time constants to 0, we get a first order plus time delay. If in addition we get the relationship between the time constant and the delay quite large, we get to an integrated plus time delay, or second order integrated plus time delay, etc. Okay, and we can consider both stable and unstable cases. So we'll start for the red case, for the base case, and then go to the particular cases. So first of all, what is the structure of the weight that we will be working with? So this is the particular structure that we will use for the weight. Okay, so the weight is structured in two parts. The first part is lambda s plus 1 over s. This is the part that will take care of robustness, and the second part with two new parameters, gamma 1, gamma 2, one of each associated to the plant time constant is the one that will take care of the set point load disturbance trade-off. Okay, so this is a more generic weight can be found in the literature. You have the reference here that for the case that you don't need to get the solution with a PID form, but if you want a PID, you should particularize to this one. Okay, so let's understand a little bit how this weight works. Okay, so what is the role of the lambda and gamma parameters? And this is very important, because in all the derivations later on, they will play the key role in the interpretation of the trade-off. If you have lambda more or less 0, the first term of the weight will behave more or less like 1 over s, one pure integrator. So for the second part, if we choose the gammas equal to the lambdas, then the overall weight will be a weight like 1 over sp. And this is, in fact, in a weighted sensitivity problem, this is a regulation specification. On the other hand, if the gamma are equal to the taus, the second part of the weights will be 1, and then the overall weight will be 1 over s. And this is a typical tracking specification. Any value in the middle for the gammas, so gammas between lambda and the taus, will get an intermediate specification for the balance between servo and regulation, and it will take care of the trade-off. Okay, so by playing with these parameters, we deal with the robustness with the first one, and then with the second one with the corresponding servo regulation specification. Okay, so if we increase the value of lambda, okay, we assumed previously that lambda was more or less 0, then the first part of the weight you will be adding the 0, and then progressively will go slowing down the resulting closed loop. So we will add some robustness. Therefore, the selected weight will allow us to deal with the two different trade-offs that we are interested in. The robustness performance, okay, and this will be via selection of lambda. And then once you have lambda fixed, with the servo regulation issues with the appropriate selection of the gammas, okay, that have this interval of allowed values for them. So it's a way of putting the specification and dealing with the trade-off inside the weight of the weighted sensitivity problem. In order to solve the problems, we need a rational transfer function. So what we do here is to do an approximation of the delay. We know that this is, okay, it's a quite usual approximation. Maybe it's not as good as I may need, but it's quite easy to deal with. We get a first order Taylor approximation for the delay. And then the weighted sensitivity problem gets, by means of application of the maximum modulus principle, gets this all-passed solution with this form rho that takes this particular expression here. Okay, so finally, the expression of the controller. I'm not providing you here all the analytical details of getting this controller. You can find it in some of the papers. You can write me, and I will send you the papers if you want it. But the important point is that with this selection of the weight and for the selection of the plant, okay, here you can see the expression of C naught, the optimal controller, as the inverse of the plant with the all-pass weight rho and the weighting function W, etc., gets the form that you get in the blue part in the upper right part of the slide. That this is the ideal form of the PID that we got, with the specific version for the eta 1 and eta 2, as you get here. Quite messy expressions, but in any case, with these expressions, you have the analytical H-infinity PID tuning for second order plus time delay plans. So in fact, this is already a first result. Okay, this is an H-infinity PID controller tuning for second order plus time delay plans. And from this generic tuning, as we go selecting the base cases, these parameters theta 1, theta 2 will get more simple versions because they will correspond to another more simple model for the base case. Okay, so this will be the place that we will, the way that we will look for the simple solutions. Before going to the simple solutions, okay, the idea is that we can make some assumptions, some simplifications to the problem. So first of all is that we got two parameters, gamma 1, gamma 2, one defined for each one of the time constant of the plan. So what's important here is that for the weight, what really matters is that we have one gamma, so 1, 0 on the weight for every plan pole for every time constant. Okay, so we can keep the same structure of the weight, but we can simplify a little bit the problem by just introducing just one gamma. So gamma 1, gamma 2 equal to gamma. Okay, and then the interval of allowed values for gamma can slightly be changed to belonging to lambda tau without the maximum time constant. So the lowest time constant is the one that matters. Okay, and then we get this as the final result that you have in this slide for statement of the problem, H-infinity problem that you solve it. The problem solution is expressed in terms of this theta 1, theta 2 that can be put into the controller solution C, and then you can interpret this controller as a PID controller, and you can elaborate the corresponding mapping for the proportional, integral, and derivative time constants of this controller. Okay, so this is the final PID tuning for this optimal controller. Okay, so now from this point we go to the specific tuning rules. Okay, so even you can see in the upper part of the slide that there are quite a few particular cases. It will be quite fast because it's just a matter of algebraic manipulations, fixing the particular case, and then solving the generic equation for the particular case. Okay, so those are all the cases that we have been considering. Otherwise, they are the most usual ones on the process industry. Okay, the main dynamics that you can find, and all the derivations go like this. Okay, so I will not go into detail in all of them because it can be very straightforward to easy, but this is the idea. Okay, so we start for the base case. You remember the red shadow at the beginning, second order plus time delay plan. How can we go for the base case to the particular case? In this case, we just set one of the time constants to 0. Okay, and we get the first order plus time delay. And then with this tau 2 equals 0, also one of the gammas goes 0. So just one gamma, we introduce these changes in the weight. And by these changes in the weight, then the final controller, it turns to be a PI controller. Okay, so finally the result is the one that you have in the lower part of the slide in the box. Okay, so this is the PI tuning for a H-infinity weighted sensitivity problem specification for a first order plus time delay plan. And the solution is expressed in terms of lambda and gamma that are the parameters that specify the weight. So playing with the weight generates directly another controller. So you can directly manipulate the controller with the meaning of the parameters lambda and gamma as taking care of the trade-off between performance and robustness and set point or low disturbance rejection. Okay, so it's a quite compact way of getting the final PI controller. You can get the same if you apply a different particularization of the base case. In this case, if you want to get an integral plus time delay controller. Okay, so you summarize the changes, you get the particular case, you apply the changes in the weight, you generate the corresponding tuning. Okay, so all these slides are optimal generic tunings, lambda gamma dependent for the weighted sensitivity problem for the particular case that is shown in blue in the slide, integrated plus time delay. Okay, second order plus time delay, this is the generic one that we got. Okay, second order integrated plus time delay. Okay, another tuning, and finally second order double integrating plus time delay. So all a whole set, all a range of tunings for all these specific cases that all originate from the original weighted sensitivity problem. So the structure of the controller directly arises from the structure of the problem solution. Okay, because the problem solution inherits the plan model and inherits the weight structure. So as you go changing the weight and the plan, then the final controller gets the corresponding structure. And the nice point is that all of them depend on lambda and gamma. Okay, so you can call the lambda gamma tuning of PI/PID controllers. So what is left from now is the second part of the talk, that where you can ask how to provide the selection of lambda gamma to get what we call a disbalanced operation. And in order to get these guidelines for lambda gamma selection, try to generate automatic tuning rules. So for each plan, what are the most appropriate values, if there are any, that gets you an automatic way of choosing them? This is the main question that we'll try to ask. Okay. In order to do this, we need to elaborate a little bit on how we will measure robustness and how we will measure performance. Okay. So in this section, we will state how we will evaluate this. Of course, there may be different ways of measuring robustness and different metrics of performance. Okay. So from this point, if you have different metrics, you can start from here and then following probably the same kind of analysis, but with the different quantitative ways of evaluation by using your metrics. Okay. Here we choose the ones that are we think that the most accepted ones in all the literature because of the meaning that they have. Okay. So let's start by an example in order to put on the table the different trade-offs that we have. Okay. So we have this first order plus time delay, and then we compare by using the previous formulas what is the result of a pure tracking design and a pure regulator design. We got them just by selecting gamma appropriately. Okay. Gamma equal tau is equal to the pure servo design, and gamma equal lambda, we are designing a controller that is more aimed to get good regulation, good load disturbance regulation. So just looking at the designs, you can see that the regulator has more higher gains. Okay, so it will be a faster design, but it will be less robust. Robustness here is measured in terms of MS, the maximum sensitivity peak. Okay, it's in this case MS equal 3 is shown in red because it's a value that is quite higher. We would not say this system is robust because it's higher than 2, and this can be also interpreted in terms of gain and phase margins, that it gives very poor robustness measures. On the other hand, the servo design is a more moderate MS value, 1.6, that you can say is a quite good robustness level. But if we look at the effect that this has on the time domain, so what are the effect of these large gains and less robust? In fact, if we compare one tracking design and one regulation design, we can see that the regulation design, the red one, is faster. Okay, you can see that the rise time is much smaller on the red response than on the blue response. Okay, and is less robust because you have a very large overshoot and some oscillations. But on the other hand, if you look at the regulation, okay, you get on the set point tracking design that is very sluggish. Okay, and this is because of the low gain. So if you want good regulation, you need high gains to get these good regulations, but you pay the price of having a non-robust design. Okay, so this is why there is the trade-off. Okay, the same can be analyzed in terms of the frequency domain. Okay, in the frequency domain, that the design is faster, basically at the end means that you have a more higher bandwidth. Okay, so the complementary sensitivity transfer function for the red design, the continuous line in red, as you can see, it is a more higher bandwidth, but you have a resonance peak that is generated by the value of MS that at the end that you have, and will generate the corresponding oscillations. Okay? So at the end, what this example shows, and the point is that this is an example of a particular situation. Okay, sorry, it is an example of a more general situation. Okay, it's just to exemplify it, but it's not just because of this example. The idea is that usually when you do a set point tracking design, it uses to cancel the slow poles of the plan always that is possible. okay? And then tries to get a frequency response that is more flat. On the other hand, regulation tries to shift and to move the slope poles of the plan, and this generates more faster designs. So at the end, and this is because the trade-off between servo and regulation, okay? At the end, when we compare between a controller design that is aimed at low disturbance rejection with a design that is aimed to achieve good set point tracking, in true what we are doing is comparing a design that is faster and less robust to another one that is slower and more robust. Okay, so we are comparing two designs that are in essence and in naturally very, very different. So the idea is to make both designs comparable. And the way that we can achieve this, we got the idea from a paper of 99 from Middleton and Grave, that they define the notion of what it's called extreme frequency equivalence. And the idea is that to make the designs comparable, we have to make them equivalent in the extreme frequency equivalent sense. And the idea is that they should have similar initial rise time and the same sensitivity or behavior in the high frequency. And the way to achieve this equivalence, at least from the perspective of our design, is to move both designs to the same level of robustness. And then with the same level of robustness, in this case, we can achieve this by increasing the value of lambda in the regulation case, such that we go and try to making the frequency response a little bit more flat, till we reach the point that both designs are comparable, okay? Something like this. So we increase the value of lambda, okay? In this case, as you can see in the set point tracking, we get lambda equal theta, and in the initial design for the regulation was exactly the same. But now we start modifying the design of the regulation. Is regulation because at the end, gamma is equal to lambda, okay? So it's a regulation design, but the initial value of lambda is increased a little bit till we reach the value of 2.7 theta, and then this makes the maximum sensitivity peak of both designs at the same value. But they take the maximum at different frequencies, so both designs will not be, of course, exactly. As you can see here, okay, even in this case, the regulatory design, the complementary sensitivity transfer function for the red design has still some peak compared with the other one that is completely flat. Okay, so in this way the designs can be compared, and this is the way in the high frequency region you can see that both designs behaves exactly the same way. Okay, and then if we compare them on the time domain, we find something like this. Okay, so we achieve the same range time, and then of course what we have been suppressed are the oscillations of the low disturbance based design, and what we have here is the reflection of purely the trade-off between the servo design and the regulatory design. Okay, so the servo design is clearly better for the set point and very sluggish for the low disturbance. On the other hand, the good low disturbance rejection of the regulatory design is paid with some overshoot and more higher settling time for the set point tracking. So by looking at values of gamma that are in the middle of the two values that you have here, gamma between tau 1 and lambda, then you can look for responses in the middle that goes balancing both responses at the same time. Okay, so this is the key point for getting the extreme frequency equivalence. And we got something like this. Okay, so this is the case that how the two parameters, the role they play in the design as we move them. Okay, so in this picture you have on the horizontal axis you have lambda. Okay, so this is the value that we fix in order to establish the initial level of robustness, and in the vertical level you have ms. As you can see, as the gamma goes increased, we go from the blue one to the red one. We go from the servo design to the regulatory design. And when we are talking of an intermediate design, this means that we are interested in getting a design that is somewhere in the middle between the blue one and the red one. And we will achieve this for gamma. So for any initial selection of lambda, we set up a starting point, and then gamma is moving between servo and regulation, and then is moving up and down. Okay, so the idea is that we can identify pairs of lambda gamma values that provides the same value for MS. Okay, and by looking at all this set of possible combinations of lambda gamma, is that you should evaluate the servo performance and the load disturbance performance of both designs and look which one is more balanced. Okay, so this is will be helping us to define what we call this lambda gamma set. In fact, this lambda gamma K set that is associated with a robustness level equal to value MS equal K. So we can define this set that will be the search set for our balance operation, for our optimization that we will define later on, okay? And this set can be defined for any level of robustness of interest, okay? So you can fix here your level of robustness and then define the search space in terms of the robustness that you desire. Now, how can we measure the performance and the balance between the servo and regulatory performance? Okay, we will use here the idea of the level of optimality, or you can interpret it as performance degradation as you move from pure servo to pure regulation. Okay, so we define here these delta S, delta R indexes that are the ratio between the integrated absolute error as a performance metric, okay, between your actual design and your optimal design. Okay, your optimal design will of course be always less than the other one. Okay, and the idea is that how if we get that this value of integrated absolute error on the denominator, the one that is IAS and not, is calculated over all the set lambda gamma K, this means that for this level of robustness is the best you can achieve for servo and is the best you can achieve for regulation. Okay, then as you move over all the set, you get balancing both of them, and then you consider what is the maximum degradation or what is the average degradation. Okay, so it's a min-max design or is an average design. These two weights, we will approach both of them at the same time, and we use both because we found them in the literature. In fact, they come from two papers that were presented in the PhD conference in Brescia in 2012. And the idea at the end will be that for most of the cases that we will find, except for some of them, it really makes not so much difference to use one or the other. Okay, so you will find probably the J max is a strategy that you can probably be more familiar if you deal with multi-objective optimization, because you have the maximum between different indexes and you want to minimize the maximum. The other gets a kind of weighting, in this case the importance of all of them, and then gets this average value. Anyway, they are different ways, they are different measurements of how the degradation between of the performance between the servo and the disturbance gets as you move between one design or the other. Okay, so it is depending on the user preferences. So from an optimization problem interpretation, this could be what we are looking for. Okay, so we will try to minimize the value of J, being J even the maximum or the average, okay, whatever, by looking at the minimum value of J over all the lambda gamma set, being the lambda gamma belonging to the specified robustness level that we have been stating at the beginning. Okay, and this is the level 1 will be the utopia point, because it will be the case where the ratio between the actual design and the optimal design is 1. So this means that you get the same performance as the optimal one for set point tracking and the optimal one for regulation. Okay, but you cannot get both at the same time. So this is why it's the utopia one. But the idea is to get as close as possible to this one. Before going to analyze the solution, I would like to highlight one point that will make us to redefine a little bit these indexes. Okay, but I could go directly for this new definition, but I prefer to let you know, to understand why we need to modify this. Okay, So let's go to the last sentence that you got in the slide, okay? That, on control, what is common sense is that if you ask for for high robustness, then this should imply low performance. Okay, you are sacrificing, at the end you're sacrificing bandwidth, and then you should get low performance. But from the figure that you have here, that is the same that we used before to explain the designs, what you find here is that as you get more robust, this means lambda gets higher. Okay, if you want a more robust design, you move lambda to values of 2, 3, 4, or even far in the right side. What happens if you move far on the right side? That the blue and the red designs gets closer and closer. So the gap between the tracking and the low disturbance ejection designs, it gets to disappear. So at that point, it will make practically no need to move from one design to the other, because both designs will be coincident in the limit. Okay, so this is misleading from this interpretation that as you move for high robustness, you should go you should get low performance. So this makes us to make a slight redefinition of the performance degradation, and to define, just instead of the level that you are working with, of the lambda gamma k, we define it as globally. Okay, so the best ones you can achieve for each one of the two operation modes. This is why you have the ratio between the actual design with respect to the global design, integrated absolute error globally. Okay, and then we use these stars to denote it. Okay, but this is the slight definition, but change, but just to let you know where it comes from. Okay, so let's go for the last point. Okay, and this last point, we use these measures to get these ideas for PID tuning guidelines for this balance operation. So first of all, what is the method that we'll follow? Okay, so I'll put this because this is the method that will be followed for every one of the specific cases. Okay, what we will do? Okay, finally, what we want is to get suitable ways of choosing lambda gamma. Okay, we got on the first part of the presentation generic expressions for PI and PID tuning rules in terms of lambda gamma. Okay, how can we provide selection for lambda gamma? Okay, first of all, we need to know, once we have the level of robustness that we are interested in, we should analyze the evolution of the performance indexes, the G average and the G max. Okay, and then we will look at the trends of this index and see where is really the trade-off. Okay, you will understand this better when we show it graphically. And look for the robustness level where we really have the trade-off between them, and look at how to select lambda and gamma by solving this problem. The idea is to collect the values of lambda and gamma for these particular solutions and see if this lambda and gamma can be given a specific closed form. Once you have this, you introduce this lambda and gamma into the generic lambda and gamma expressions that we got at the beginning, and then you will get the corresponding automatic tuning. Okay, so what are the kind of graphical, because we will show it graphically because it is much more easy to interpret. Okay, though this is the kind of picture that we will see from now on to the end. Okay, this is the picture that allows you to see the trade-off between performance and robustness. And the nice thing here is to interpret the graphics. Okay, as you can see, we are interested in the ways where the slope is negative or zero. Okay, in the picture you have it, the circles in the 1.6. What happens in this point is that if you increase a little bit robustness, so you move a little bit to the right, then the performance decreases quite fast. And if you reduce robustness just a little bit, then your performance, okay, reduces also, because you get to quite higher values. So there is a trade-off here. But if you go to the right part of the slide, and you are, for example, in 2.4, in this part, you don't have any trade-off, because you can at the same time improve robustness and performance. So there is no robustness performance trade-off. If you are in 2.4 and you move to the left, at the same time, you will get a system that is more robust, less values of MS, and at the same time, it is with higher performance because the level of the, or the values of the cost function will go with lower values. Okay, so this determines what are the areas of the graphic that you need to work with. Also, you have here plotted at the same time the SER1 regulation, blue and red degradations, okay, and also the J max and J average indexes. As you can see, the average, that is the dashed dot line, is always in the middle of both, okay, because it gets an average, and the max is coincident with the maximum value for every value of robustness to the maximum value of 1. Okay, so in this case, in this particular case, you can see that, for example, a value of MS equal to 1.6, it provides a point when you have a good point for the trade-off here. Okay, and also you have a separation, you have a gap between the blue one and between the red line. So if you have a gap between both, this means that you have a trade-off between both designs because the level of performance is different on both. Okay, so this is the kind of pictures that we work with, and we will work with for every one of the plant families that we have. Okay, so the discussion on the presentation, you have all the considerations. Okay, so in order not to be too much longer, here I will do the analysis for the first case, and then from this one you can follow all of them. Okay, because all the kind of analysis is completely similar. Okay, so when we are saying for the plant family, what we refer to, okay, so this is the case of stable and integrating first order processes. Okay, as you know, first order plus time delay processes are characterized by the normalized t-time constant, okay, theta over tau, that is represented here. So this adimensional constant provides you a way of parameterizing your process, and then you have it here for values of 1, 0.2, 0.1, or 0. Okay, the case of 0 is where the time constant is infinite and you go to the integrating case. Of course, you can get much more cases in the middle. This is just to show you but if you get, you know, more smaller, more shorter steps, you get a more well representation of the plant family. Okay, so the idea is that you can see that what changes in any one of the pictures is that the slope goes changing. Okay, the gap, so the difference between the SER1 regulation gets higher as you move to the integrating case. Take care of the scale of the vertical scale for the performance. Okay, for the first figure, you see that is between 0.8 and 1.8, and in the last one for the integrative case, you go over 8. So the gap between the red and the blue one is much higher. And in fact, the kind of plans for those that you have really the trade-off between several regulations are the ones that are the integrating case. Okay, so what is the conclusion that we can follow from all these cases? That while keeping in the first order plus time delay, as you move all over the family by testing different cases for the normalized dead time, you can see that the value of robustness 1.6 in all cases provide a point where you have a good choice for the trade-off between server regulation. Okay, because the point where you move on the left or on the right, the 1.6, then you go increasing or decreasing the performance. Okay, so this suggests that we can choose 1.6 as the level of robustness to look for the automatic tuning. Remember that we are doing this in order to get the automatic tuning. Okay, you can think now that I am doing quite a lot of simplifications here, and this is why at the very beginning I was stating that probably we are not looking for the most optimal design, but for suboptimal ones, but to get more simple expressions. Okay, so we get fixing 1.6, and for every system for different values of theta over tau, or for the normalized dead time constant, we get what are the corresponding values of lambda and gamma, and then we get the following representation. Okay, so in this case, I see that some of them cannot be seen right now quite well. I don't know if it is because of the, sorry for this. Okay, so, okay. Yeah, this one is better. Yeah, it's the same. I think something I changed it. Okay, so it's just to show you more the example how we collect the values, and then we put the values in the form of tuning. Here you have the information to both indexes, max and average. Okay, so the same kind of analysis. As you can see, for the average, the final values are more simple. So for both cases, you have different cases for the normalized dead time, theta over tau 1. Okay, you can get much values in the middle, but it's just to show you the trend. Okay, and what you can see is that for the values of lambda and gamma that provide you the value of 1.6, okay, the values of the optimal set lambda gamma over k, then you have that the gamma over lambda are more or less 1 on all the cases. So the selection suggests gamma equal to lambda, okay? We are on the right side right now. And for what matters to lambda over theta, for the average index, you see that the cases are more or less between 2 and 3. So here we choose, okay, one value in the middle, 2.5. Okay, again, here we are for simplicity. Okay, so we got, the idea for us is to get very simple choices. And we follow similar rules for the case of the J max. Okay, you can see that on the J max for the lambda over theta, we are approximating more or less lambda equal to 1.25 theta, and then for the rest, lambda more or less 9 lambda, etc. It is just for the values of on the gamma lambda ratio that have a really very different trend that we need to get a rational polynomial approximation, because if not, we will completely, in this case, lose the performance. But on the other case, the approximation of 2.5 is more than reasonable. Okay, so you get practically no losing of performance in this case. And then you take these values. Okay, you take these selections that you have on the dashed box here, and you put these ones on the corresponding formulas. So the final result is that you have the blue box here, okay, for the two base cases, first order plus time delay and the limit case of integrator plus time delay. And then depending on the way that you want to evaluate the balanced operation, you should use the selection for the average, or you should use the selection for the maximum one. Okay, and then you have the appropriate values for lambda and gamma. As you can see, for the average, the selection is the same for both first order plus time delay and integrator plus time delay. But for the case of J equal to J max, you have different selection for the case of first order plus time delay and for integrated plus time delay that is much more simple. Okay, so finally, you will get a tuning rule that is completely automatic because you already have the selection for lambda and gamma, so no free choice, completely automatic, and just with the parameters of your model, just by theta, the delay of your model, and tau, the time constant of your model, you put them here and you get your PI. Okay, and this PI will be the tuning guideline that we are providing you in order to get a robust system, because MS is equal to 1.6 and with a balanced operation between set point tracking and load disturbance. Okay, for these cases. And then you will have exactly the same for the unstable cases. You get the similar case, similar analysis for collecting them and getting the corresponding tuning. Okay, and also for integrating processes, etc. Okay, so I will just not follow them because it's to get repeating the analysis for all the cases, and then you can follow it. And also, if you are interested, I can provide you some papers where this is presented. Okay, so just to conclude, what we have seen here is in fact that it is possible to approach the PID design problem with a modern perspective. Okay, so classical controller with a modern point of view. We have stated the problem by a change of a scenario. So we get a 2-parameter space design lambda gamma instead of the original 3-parameter space. And the treatment has been stated by starting from a unifying approach, getting what we initially called the red shadow base case, and then going to the set of different process dynamics of particular cases, the one that were green shadow. Okay, and it turns out, even we have not been on this topic on the lecture, that this particular selection also you can recover some tunings that there are already around there. For example, if gamma is equal to tau, then what the final tunings that you get are the ones that are usual for internal model control designs that you find on the literature. Okay, so it is quite nice, this one. Regarding to the performance indexes, so we use both of them. Okay, average usually goes for regulation designs. Okay, and the maximum tends to be a little bit more sacrificing the regulation operation and get a more balanced trade-off. But the point is that for the dynamics that goes difficult to control, I mean unstable dynamics or integrated systems, both cases, so independently on the index that you use, J max, J average, what is suggested is to go for regulation design. Okay, so regulation design in practice is the usual operation and the usual tuning preferred. So common practice is to consider low disturbance, low input disturbance, and this is what is suggested from the analysis that we have found here. Okay, and also from this one, okay, we have been analyzing different cases, but of course there are more. We have not considered, for example, oscillation dynamics. What happens if the plant has complex poles? Okay. Also, we have been using one specific way of measuring the robustness and measuring the performance. You can get other measures, okay? So you can follow the same kind of analysis, but by using different ways of evaluation. And of course, the formulation of the PID, okay? The formulations of the PID, we use the ideal one with filtering all the computations, okay, to get a little bit more real, but you can use other more practical formulations for the PID, okay? For example, the series one, or the PID with filter, or the double filtering, reference output filtering for the PID, etc. You get a more spaces, more parameters from the PID, okay, but probably you will get more practical information. In any case, the problem obviously will be more difficult to face if you have more parameters with the final controller. So most of the presentation that you have seen here, so you can, it's on some papers that have been already published in Journal of Process Control or engineering and EAC research, okay, and also it has been the topic of a book that we have been publishing and has been out by CRC Press this February, so it's out there, and you can see the main topic is the approach by using the weighted sensitivity problem. So a much more detailed is from there. In any case, if you are interested, just drop me an email and I can provide you some of the documents and some of the information if you are interested. Okay, so again, thanks for inviting me. Hope the talk has been motivating you even if you need to apply the PID, or even if you need to do some research on PID. Okay, so thanks again.